Hello and welcome back to another video about the VIC II. So I think I will film the screen like this. Don't you think it's great? Of course, I'm just kidding. I have a OBS set up here over my command TV. You can see it over here. Haha. There you go. Yeah, so welcome to another video. And last time we looked at the VIC chip. We have slowly find the address decoders, which is here, and we found some here. I have later found that there are the decoders are here, but there are the registers that we found here and here. There are also some just registers here, and these are the ones we're going to talk about today. They are the enable registers. So, and there's also one up here though, because I think they didn't have the space down here for some reason. So we'll ignore that one. So yeah, so here we have the diagram. We have the counter, and we have looked at the counter, and we have the ROM, which makes control signals while the counter is stepping through the addresses of the room. And then we looked last time at this part over here. We found that we had a decoder that says 112. So this is the raster. So we found out that this is the raster register over here. And I got a note from the Highlander saying that remember that there are 9 bits in the raster. So yeah, you had raster 0 to 7, so that's 8 bits. But you have also this is the 12th register, but this is the 11th. And in the 11th registers I have several things. But you also have raster 8, which is 9th bit. And if you look closely, you will see that the raster 8 is connected to the 9th bit of the counter. So yeah, so here's the 9th bit. And you can see it here, it goes down there and there. And it's connected to the comparator of the 9th bit. And another thing, you can see that you see this yellow line going here. It's the output of the comparators. So if I make the opacity a little bit lower on the background image, you can see it's the output of the comparators for this raster register. But this control register, which is called, which has the raster 8, it has also a comparator. So that output of that comparator is then connected together with the output of the other registers, comparators. So they are together. So if the 9th bit doesn't match the 9th bit of the counter, then this one will pull this long line low. And I have called it RC on master. So, and today I wanted to show you the IRQ logics of the IRQ, and I want you to see how I can simulate it. We can reverse engineer and simulate it and see it actually works and what all the stuff in there is. So the reason for me calling it RC on raster, you have a counter on the right side of this screen. And this counter, whenever that counter is matching the comparator or the raster register, then we can say that we have RC on raster. So the counter I have called RC. So RC stands for row counter or raster counter. So that's the horizontal counting. So there's a lot of counting in the vertical before the rows are incremented. So therefore also this counter must have an halt. It must stop whenever it has counted one step, incremented once, because it can only increment when there's a new line, right? So we will look at that. So this counter must have an halt input or enable. Okay, so let's follow the RC on raster. So here you can see the output of the raster, and it has a buried contact here on a polysilicon, which is not used as a transistor in this case. It's just a via, because there's no diffusion network around here. So we can see that it passes all the sprite registers, and then finally it enters the last part here, which is the decoders for the interrupts, which I figure out. So we have the address bus coming in here, and we have these decoders that we looked at last time. And here you can see the light pen decoder. So before we go to the interrupt, let me just show the light pen functionality. You can see that it gets the the counter bits, like all the other registers does. Like this one has a comparator, but the light pen, if you look closely, it doesn't have a comparator. The comparator looks like this, with like this snaking. Anyway, but the light pen isn't, because it's not used for comparing. It's used to store the what shall I say? It's used to store the current raster or row whenever the scan line or the electronic beam hits the light pen. Then the light pen will send a signal, which comes here somewhere, I don't know, I think maybe here, and it will then latch or load that counter value, and it will save that in this register, so that the CPU can then load the register the value from this register later. So yeah, and I'm not sure if there's a interrupt on that one. So okay, so I pull the RC and raster over here, so you can see, or the marker up here, so you can see it. So now I think I will show you it in a picture instead, what we are doing. So what we're going to do is that the RC and raster, which is supposed to give you an interrupt whenever the RC is on the raster register value. So here is that one is produced, and then it's routed over here and into this interrupt latch and enable register, and then whenever this logic is satisfied, it will then produce a IRQ, which goes out here. Don't remember who this, I think it's this one. So that's how it works. So there's a logic element up here. Okay, so I open another document because which is smaller, because it's slowing down such that I can't zoom so fast, but now I can zoom faster. It's just a cutout. So yeah, so here you have yeah, I can tell you, finding out where the diffusion goes here. Well, here it was okay, but when you get up here, that was really hard, especially in these registers up here. What you're looking at now, here are the address bus, and these are decoders, and we can ignore this. This is light pen address, and here you have the coder for 18, 19 and 1A. So 19 and 1A are the ones that are interesting now. Here you go. So 19 is interrupt register and 1A is enable. Interrupt and enable. So in order to remember that, I have put some blocks here. How about that? You have 1A which produces this part, and 19 which produces this part. 18 just passes through here, as you can see, and continues, so we will ignore that one. And how do you know that the RST or raster is on the first bit, or 0? Yes, that's because you have data 0 coming in here, so therefore I know that. And when you look at stuff like this, it's better to look at the output first. So, and we know that the line here goes down to the IRQ. And I bet you a bottle of Coca-Cola that this line and this line was connected somehow, and they are. So I think I win. So the output is then here, and here you can see the output. And notice how this is the output of all the, it's the output of all the interrupt registers, including the enable. So yeah, because the enable register will then activate this gate, and for it to draw the IRQ down, you will need to you will need a path here, right? So therefore enable must be on, and then the IRQ or interrupt latch must then be or set. And why do I call it a latch? And how did I know it was a latch? Well, there was a clue in here. So there are 4 interrupt sources in the VIC. Every source has a corresponding bit in the interrupt latch. So it's a latch then, register D19, which is here, down here. So this must be a latch then. And a bit in the interrupt enable register 1A. When an interrupt occurs, the corresponding bit in the latch is set. To clear it, the processor has to write a 1 there by hand. And the Highlander gave me a code where he had an ASL, or acknowledge, I think. And I think what actually happens is that what they say here, the processor has to write a 1 there by hand. The VIC doesn't clear the latch on its own. Yeah, so what happens then? If at least one latch bit and the belonging bit in the enable register is set, the IRQ line is held low, and so the interrupt is triggered in the processor. So the 4 interrupt sources can be independently enabled and disabled with the enable bits. As the VIC, as described, doesn't clear the interrupt latch by itself, the processor has to do it before the high flag is cleared, respectively, before the processor returns from the interrupt routine. Otherwise the interrupt will trigger again immediately. So here you have the memory element that the processor can write to enable. And over here you have the input, so such that you can not you actually, it's the VIC itself that has to have an input such that it can set the latch. So yes, I want to show you how that works. We can look at it like this, but it gets confusing pretty quickly. The first thing you can see here is that the RC on raster signal comes in here, and there's a line here. And this line, it's called it's phase 2 clock, I think. So okay, so we have the RC on raster coming in here, and it has to pass through a gate here, a transistor, which the gate is actually phase 2 of the clock. When this clock is off, who is driving this this gate, it's floating. It was one of those demos on YouTube where where a guy is on a stand and he tells you he can use an emulator and he can freeze at any time in the code and see the state of the registers. But you can't do that in hardware because, well, you can do it if they say that the ship is fully static. And sometimes you can see that in the title of a datasheet, that this ship is fully static, so you can single step. But here, if you do that, the charge that's on this gate, it will go away. So, or yeah, disperse. So it won't work forever. But since this one is running at a high frequency, then it will stay on until the next clock phase. So you can look at this as a flip-flop actually. So this gate is loaded each time there's a clock phase. So when we're going to model this, I will use a flip-flop. So what you can see, the RC on Raster comes in here. You have a ground here, so you can pull. Draw it. You can pull this net down here, which means you can also pull the red one down. Right? And also you see this RC on Raster, this bypasses this gate, this clock gated flip-flop thingy up here. So you see this output of this flip-flop here, it can drive this one, and but at the same time before the flip-flop it bypasses and then drives this one. So what the hell is going on here? Well, this part here is not connected anywhere else, so this is just a intermittent stage. So now we come into NMOS logic, so let's have a look at that. So if you know logic gates, you have like an AND gate, this, A and B, and F. And F is now A and B. So if both inputs are on, then the output is on. If not all of them are on, then the output is low. So we have an AND gate here. So in hardware it would look like this. You have the pull-up resistor, and then you have the two transistors, and then you have ground. These are the two gates, not the best transistor in the world. And here's the output. So this is A and this is B. So this is NMOS logic. So this is an AND. No, sorry, NAND. This is a NAND gate. Okay? Because both of these must be on for the output to be active. Or low though, because it's a NAND. If you drop the NAND part, then we should have a high output when both of these are on, but this is not the case. This is a NAND. So therefore you often see a negative logic like this. Okay, so this is an AND gate. So this and this must be on for this one to be low. Or this one. So you can see it gets pretty fast confusing, so let's just remedy that. We have a cool tool for that, and it's not really recommended to use, but as a teacher or as a student you can learn a lot by using it. So it's too simple actually, but for this task we will use it such that we can learn something from it. So let's try and figure out what is what. Okay, so what the first we are seeing here, we see a gate, which when the clock is low, it remembers what was on this line. So if it was a 0, then it remembers the 0 when this gate goes off. So we need a memory element, and for that I'm going to use a flip-flop, and the RC on raster input signal, I'm going to just use a switch. So if I switch this on, then we have a raster on the interrupt. So so we're going to make it simple today. So let's have a let's put a label here. And also we will need a clock. The problem here that we don't have a actual two-phase clock, so for now I'm just going to give it a clock, so you can see that it's ticking away slowly. And before I do anything else, I can show you how it works. This is how simple this program is. You just drag in a light bulb, and when the light bulb is on, then you have active output. So now the light bulb is red, that because this program doesn't know the internal state, because it hasn't been cleared or set yet. So here we can see that the output is high because it had copied the D input. So what's the point in that when the output is the same as the input? Well, it's not the same all the time, that's the point, because it will only be high when there's it will only copy when there's a positive edge. So you see nothing happens here, but it happens when you give this a positive edge. Well, there's no positive edge here, it's just on, so that's the difference here. So but we will use it like this, so it's okay. So let's remove this one and continue our journey. Yeah, so the first thing we can see that this is like an inverter. So let's have an inverter, because this gate can drive this. When this is 1, then the output is low, so that must be an inverter then. Actually, you don't need the inverter, you could just connect to the inverted output, and we can see that this output of this inverter is now going down here. It can't drag this output over here down unless this one is also on. So this one and this one, A and B. So therefore use the AND gate. Simple as that. And where does the input of the other side of the AND gate go? Well, that's here. That's the RC and raster, which is here. Simple, simple. So what is the point of this then? Why have they done this? It's like a one-shot. So if I clock this through, you can see nothing happens. But if I turn it on, then it's on only when the clock is low. And then once the clock comes again, then it switches this off again. Nothing happens until there's a positive. Oh my god, now I have recorded like 20 minutes, and what you see on my webcam here, it hasn't been in the recording area of my screen, so whoops. Okay, I did reverse engineer, but what I want to do now is to show you what I did instead of doing it again. Because one thing is it takes time, but also easy to make mistakes while you do it. So now I've done it, so I can explain it. Right. Done that to begin with. I should have done this. Oh, been there, done that. Okay, so we ended up here. We needed a OR gate with a ball. Okay, so because we have these two ANDed, or this one, will then produce a negative output, so therefore we needed a ball to signify that. So we reversed engineered this one, and then we saw that there was an output here also that was connected to this gate that controls the first output. So here you go, you can zoom in on it. Here comes the first flip-flop in here, inverter, and that signal is ANDed together with the same signal, just that it is connected before the flip-flop. So therefore you have it before the flip-flop, right? RC and raster, and together with this gate here, they are ORed, so they can control this output. So it's this and this, or this and this, or this. So you have 3 inputs to that. And you can already see that I have a latch here. So how did that work out? Well, to make that latch, we need to see... Yeah, we have to follow the output here and see where that goes. And we can see that the output here drives this gate, and the output here is driving this gate. So we see there's a sort of a ring going on here. So yeah, so this output here, this output, it's here, and it goes into this one, which is an input to this one, right? So therefore we have an OR gate here. So this is also an OR, because either this one or this one can make this green part here go low, and then when they go low, then you can pull this low, or you can pull this low, which can pull this gate low, which is the first output. Rightio. So let's zoom it out so you get some more into the screen here. Okay, and what is that? If you've seen that before, you know what it is. So let me just show you how that works. So, and you probably know what this is already. So if I now bring in a switch, 2 switches, this, let's see, you can set it and reset it. And what is set or reset, you can define yourself. So it's completely symmetrical. So if you bring in a lamp here, set, reset. Doesn't matter how many times I click it, I can set it. So yeah, so we have a latch here. Let's call a latch. So the latch can be set. So if there comes a RC on raster, let me click it. Like this. Now we can see it was set. It didn't work as expected, so I have made a mistake here. I think I'm missing a inverter here. But the thing is, this is supposed to be 1 when it's going to reset. I did something wrong here. So okay, so I seem to be missing an inverter over here. So don't remember why. This. And these 2 phases are ticking away, nothing happens. So let's say the processor writes a 1 in there, and then there it's reset. And then you have to pull this down again. And then after a while, the raster equals the RC, so then it's set. And then you see the latch is set, and then processor resets it, or acknowledges it. this. So now it works. Now we have a circuitry that can set the latch. So it's you can think of this circuitry as a one-shot, because now this one is on and it's setting the latch, and when you push this button here, that means you get a clock phase 1. You see that it turns off again out here, because the input is now shifted out. So if I go back again and click away, nothing happens. And if you open it, you see that the output there is on, but only for a moment. So you can look at this like a edge detection circuitry. So, and you can see all of this is reflected on the IRQ output over here. So there are more things we can reverse engineer here, but shortly you can see that this is a memory element like we looked at last time, and the computer, the CPU can write a bit in here, and with the right what is it called, right strobe, you can then copy this bit in though. So, and with the read you can get the value out again on the data bus, and then the stored bit will then control this enable functionality. So, and you can see here that for this IRQ output to be activated, you need both enable and the latch to be set to make a path down to ground. So therefore the output is low if latch and enable is on at the same time, and therefore you have so you have the latch here, and you have an AND port because I say AND and the enable bit for the raster, and I've been lazy here, I've just used a switch, and the output here is then ORed together with the other interrupt register, because it's not only the raster, as you can see, you have other registers over here, 3 of them, and there's another one way up here also, the 4th one. So, but if I set the latch, let's say there was a RC on raster, IRQ is not activated, because IRQ low should then the lamp should be off. The lamp shall be off when there's an IRQ, but it's not. But that's because we haven't enabled that bit. So if the CPU writes a 1 in this register, you can see how that works. So this AND gate is used to sort of open the gate for this signal to come through. So if you turn it off, then this is no longer on the output there. So the output, the IRQ is not affected. But if you enable it, then it's potentially then it's possible to get an interrupt on the IRQ though. So let's say we are on our raster again, check down, and it checks away, and you can already see on the right side that the IRQ is now active, because the lamp has run out. That's why I'm using this hash symbol to signify that when it's off, then it's active. I can reset it, so the CPU writes 1, and then it's clocked in here. The CPU turns the bus off again, and you can see the lamp has come on again. So that means there's no IRQ anymore. So I'm doing this over and over, because it's a little bit fun to see that it actually works, you know. Next time we'll be looking at something more interesting. So we have our digital works there. I can just give you a little taste of it. So we have a cool program called Digital Works, and this is a reverse engineering of what I think is the counter, and it works like a counter, so it must be a counter, right? You can see tick 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 tick. So this is the two-phase clock. This Digital Works is much cooler for yeah, you can make more accurate digital circuits with it. So, and now I was talking in the beginning about a counter that had a enable pin input. So when I switched that on, the counting stopped, but the clock is ticking away here, as you can see. So if I switch that off again, you can see that the counter is counting. So yeah, so we will look at that more next time. So, but the counter is actually 9 bits. So yeah, now you can see it chugs away, and here is the broom. You get in there and put in values. For example, yeah, 137. That was like the end of the border, I think. And then one of the outputs is going to be high, and then one at 135. There's another one. So yeah. So that will be interesting. So, and you can also, while this is running, you can get into one of these macros that I made because they are the same. This counter has like, is it like 4 or 5 or 4.5 of the same circuit? Therefore I made one and then copied it. So while this is simulating, you can get in there and see what's actually happening inside the logics. And you can see it's pretty simple when you get down to it. So yeah, so okay, so thank you for watching. I hope you liked it, and go try it logically. So it's fine for doing simple stuff and to learn digital electronics. So you can also play with you have set reset flip-flops with a clock input, but this one doesn't have a clock input though. So, but this one has, and yeah. So play around, have fun. Thank you for watching. Bye bye.